The universe hums with secrets just beyond our reach. Right now, we will explore 40 astonishing patterns in the behavior of the smallest particles, clues that point to a hidden order woven into the fabric of reality itself. By the end of this journey, you will see the cosmos in a completely new light, understanding why these tiny anomalies could rewrite the fundamental rules of physics. We will travel from the bizarre quantum foam to the vast cosmic scale, asking why a heavier cousin of the electron wobbles unexpectedly and how the emptiness of space holds an energy that defies all logic. These are not random glitches but fingerprints of a deeper symphony. What does it mean for our reality if the rules we know are merely the surface of something far grander? That same drive for order has burned within us for millennia. Long before we had particle accelerators, Greek thinkers like Democritus stared at a slab of marble and wondered if it could be divided forever. He proposed the atom, an indivisible unit, the fundamental building block of all things. This was the first great guess at a hidden architecture. Centuries later, Isaac Newton gave us a universe governed by elegant, predictable laws, where gravity and motion followed equations as precise as clockwork. The cosmos seemed to be a machine of perfect order. Then came the 20th century, and with it, quantum mechanics. The predictable clockwork universe vanished, replaced by a realm of probability and ghostly waves. Particles could be in two places at once, their exact paths impossible to pin down. This new reality was so unsettling that even its architects were troubled. Albert Einstein, who helped birth this revolution, could never accept its inherent randomness. His famous objection that God does not play dice with the universe was not a theological statement but a profound belief in an underlying determinism. He was convinced that the quantum weirdness was merely a veil, hiding a deeper, more rational layer of reality that we had not yet discovered. This epic search, from the philosophical atom to the quantum dice game, sets the stage for everything that follows. The 40 patterns we are exploring are not isolated curiosities. They are the latest clues in this ancient detective story, tantalizing hints that Einstein might have been right all along. They suggest that the strange, probabilistic rules we currently accept are not the final word, but merely the surface ripples of a much deeper, more elegant order waiting to be found. But what exactly are we looking for when we say we have found a pattern? In the everyday world, a pattern might be a repeating design on wallpaper or the predictable rhythm of the seasons. In the quantum realm, the definition becomes far more precise and profound. Here, a pattern is not merely a repetition. It is a consistent, measurable relationship that emerges from the chaos of raw data. It is a specific symmetry that nature stubbornly preserves, a statistical correlation in the decay of a particle, or an unexpected alignment in how fundamental forces interact. These are not accidents. They are the subtle fingerprints left behind by the underlying laws of the universe. Often, these patterns are impossibly faint, visible only when we compile and analyze staggering amounts of information from colossal machines like the Large Hadron Collider, or from painstaking observations of cosmic rays striking our atmosphere. The monumental task for physicists is to distinguish this faint signal from the ever-present background noise of random events. This requires unprecedented technological precision and sophisticated statistical methods, a constant battle to separate cosmic whispers from meaningless static. Understanding this rigorous definition is the essential first step. It transforms our list from a simple catalog of curiosities into a collection of credible clues, each one a carefully documented piece of evidence pointing toward a hidden cosmic blueprint. This slight but stubborn wobble of the muon is our first and perhaps most compelling clue. Imagine a tiny, spinning top placed within an incredibly powerful magnet. According to our best map of physics, the Standard Model, we can predict with exquisite accuracy exactly how that top should wobble as it spins. The muon is that top, and for decades our predictions seemed flawless. But then our measurements became more precise. We built machines like the one at Fermilab, capable of holding this dance in a magnetic field more stable than any ever created. And there it was, a whisper of a difference. The muon wobbles just a fraction more than it should. Scientists call this the G-2 anomaly, a name that belies its profound implications. This is not a measurement error. It has been confirmed and reconfirmed. It is as if, within the perfect vacuum of the experiment, an invisible hand is giving the muon an extra, gentle push. What could that hand be? The most exciting possibility is that the muon is sensing particles or forces that are completely unknown to us, shadows from a deeper layer of reality that our current theories simply do not include. This tiny anomaly is a crack in the foundation of modern physics, and through that crack, we can just begin to glimpse the light of a hidden order. That subtle extra wobble in the muon suggests unseen forces are at play, but it is a clue that remains frustratingly indirect. Our second pattern, however, strikes at the very heart of our own existence. It is found in the fleeting lives of particles known as mesons. When these particles decay, they offer a glimpse into one of the universe's most profound imbalances, the subtle but absolute preference for matter over antimatter. The laws of physics, as we understand them, treat matter and its mirror image, antimatter, with an almost perfect symmetry. For every particle created, an antiparticle should be born. When they meet, they annihilate in a flash of pure energy. This elegant balance presents a cosmic paradox. If the Big Bang created equal amounts of matter and antimatter, they should have completely obliterated each other, leaving behind a universe of empty, sterile radiation. And yet, here we are in a cosmos filled with galaxies, stars, planets, and life, all made from matter. Something in the earliest moments of time must have tipped the scales. This necessary imbalance is known as CP violation. It is a tiny but crucial crack in the perfect mirror of nature, allowing matter to gain a fragile upper hand. Our standard model does include a mechanism for this, but it is far too weak to account for the vast, matter-dominated universe we see today. The pattern emerges from experiments like LHCb at the Large Hadron Collider, where physicists meticulously track the decay of trillions of mesons. They have found that the asymmetry in how matter and antimatter versions of these particles behave is stronger than our theories predict. This is not a minor discrepancy. It is a direct challenge to our understanding of why anything exists. The heightened level of CP violation points toward new physics, perhaps exotic particles called leptoquarks, or even additional types of Higgs bosons, that could have provided the powerful shove needed to create our material world. In the delicate decay of a single, unstable particle, we may be witnessing the faint echo of the process that made our entire reality possible. This imbalance in the very rules of existence is a puzzle on the grandest of scales, but our next clue forces us to peer into the heart of something seemingly familiar. Every atom in our bodies contains protons, the stable, positive anchors of the atomic nucleus. For decades, we pictured the proton as a simple, spinning sphere, much like a miniature planet. Its spin is a fundamental property, as intrinsic as its mass or its charge. And for just as long, we thought we knew exactly what gave it that spin. Protons are made of smaller particles called quarks. It seemed perfectly logical that the spin of the whole proton should simply be the sum of the spins of the quarks inside it. This was a cornerstone of our understanding. Then, in the late 1980s, an experiment called the European Muon collaboration delivered a result that sent shockwaves through theoretical physics. When they measured the proton's spin, they found that the quarks themselves were responsible for only about 30% of it. The quarks, the very things we thought were doing all the spinning, were barely contributing. This was not a small margin of error. It was a fundamental collapse of a basic assumption. an event so dramatic it was immediately dubbed the proton spin crisis. Where was the missing 70%? If the quarks are not providing the spin, what is? The immediate suspects are the other inhabitants of the proton, the particles called gluons. Gluons are the carriers of the strong nuclear force, the incredibly powerful glue that holds the quarks together. They are constantly flying back and forth between the quarks in a frantic, energetic dance. It is possible that the orbital motion of both the quarks and the gluons, their frantic whirling inside the proton's confines, contributes significantly to the overall spin. But when physicists painstakingly measure these contributions, the numbers still do not add up to a perfect 100%. The crisis remains. This is not just an accounting error inside a single particle. The proton's spin is a window into the chaotic, seething reality of the quantum world, a place where simple analogies completely break down. It tells us that the proton is not a neat collection of billiard balls, but a dynamic, turbulent storm of energy and force, governed by interactions so complex that our current mathematics struggles to describe them. Solving the spin crisis is essential to truly mastering the strong nuclear force, the very power that builds atomic nuclei and makes our material world possible. The missing spin is a direct signal that a deeper, more complete theory of quantum chromodynamics is waiting to be found, one that can finally map the hidden whirlwind at the core of every atom. If the proton's internal chaos reveals a hidden whirlwind, the next pattern confronts us with a puzzle of cosmic stability. The Higgs boson, discovered after a 50-year search, gives mass to the fundamental particles. Yet its own mass presents a paradox so deep, it challenges the entire framework of quantum field theory. The problem is one of balance. In the quantum vacuum, virtual particles constantly flicker in and out of existence, and these fleeting fluctuations should violently interact with the Higgs field. This interaction should drive the Higgs mass to an astronomically high value, up near the Planck scale, which is the energy level where gravity becomes as strong as the other forces. That scale is a 1 followed by 19 zeros larger than the mass we actually observe. For the Higgs mass to remain at the relatively low electroweak scale we measure, an almost perfect cancellation must occur. The positive contributions to its mass must be precisely counterbalanced by negative contributions, canceling out to an accuracy of 1 part in a million trillion. To a physicist, this degree of fine-tuning seems unnaturally perfect, as if the universe's most fundamental parameters were dialed to an impossibly specific value. It is like balancing a pencil perfectly on its tip, not for a second but for billions of years against a constant hurricane of quantum noise. This is the hierarchy problem. The pattern is not a single measurement but the stark, unsettling fragility of this entire energy scale. Why is the universe structured with such vast, unexplained gaps between the strength of its forces? The most compelling idea to resolve this is supersymmetry, a proposed deeper symmetry of nature. It suggests every known particle has a heavier super partner. The contributions from these partner particles would naturally cancel out the quantum corrections to the Higgs mass, making its stability elegant and inevitable, not a miraculous accident. While evidence for supersymmetry has remained elusive, the fine-tuning of the Higgs remains one of the strongest indicators that our current model is incomplete. It points toward a more profound principle, a hidden mechanism that protects the scales of our reality, waiting to be discovered. This fragility of the Higgs points toward a hidden symmetry, but our fifth pattern emerges from a particle that seems to defy symmetry altogether. Neutrinos are the ghosts of the particle world, streaming through you by the trillions every second, interacting with almost nothing. For most of the 20th century, our theories insisted they had to be massless, like particles of light. This was a tidy, elegant idea. Then reality intervened. Experiments observing neutrinos coming from the Sun and the upper atmosphere revealed something astonishing. These phantoms were changing their identity as they traveled, a phenomenon called oscillation, a neutrino that starts its journey as one type can arrive as another. This is only possible if they have mass, however tiny. The discovery was monumental, shattering a core assumption of the Standard Model, but the mystery only deepens from there. The masses of neutrinos are not just small, they are absurdly minuscule. The electron, the next lightest particle, is at least 1,000,000 times heavier. Why is there such a vast, unexplained desert between the mass of the neutrino and the mass of everything else? This is not a minor detail, it is a chasm in our understanding. The pattern of their masses and the specific ways they oscillate do not fit the tidy patterns we see with quarks and other leptons. It feels like a message written in a code we have not yet broken. One compelling idea to explain this is the seesaw mechanism. Imagine a playground seesaw with a very heavy child on one end and a very light child on the other. A small push on the heavy side creates a large motion on the light side. In this cosmic analogy, the light child is our familiar neutrino. The heavy child would be a hypothetical, incredibly massive sterile neutrino, a particle that does not even feel the weak nuclear force. The existence of such a behemoth would naturally explain the feather-light mass of the neutrinos we can detect. This mechanism ties the infinitesimally small scale of neutrino mass directly to a physics operating at almost unimaginably high energies, energies that may have existed only at the very birth of the universe. Every time a neutrino changes its flavor during its oscillation, it is not just a random quantum flip. It is a delicate dance, its rhythm dictated by the mass differences between these states. This rhythm is a direct signal, a whisper from a hidden, more fundamental order that governs particles at energies our colliders can only dream of reaching. In the silent, ghostly journey of the neutrino, we may be receiving our clearest postcard from the edge of known physics. The ghostly lightness of neutrinos hints at a hidden architecture, but our sixth pattern reveals a flaw in the very foundation of reality itself. It concerns the energy of nothingness, the vacuum of space. According to quantum mechanics, empty space is not truly empty. It is a seething, bubbling sea of virtual particles that constantly pop into and out of existence. Every cubic centimeter of this apparent void should be crackling with an unimaginable density of energy. This vacuum energy, known as the cosmological constant, should have a colossal effect on the universe. It should generate a repulsive gravity so powerful that it would have ripped the cosmos apart in an instant after the Big Bang, preventing any galaxy, star, or planet from ever forming. Our most careful calculations predict a value for this energy that is a 1 followed by 120 zeros larger than the value we actually observe. This is not just a small error. It is the single worst prediction in the entire history of science. The universe we live in is only possible because this vacuum energy is almost, but not quite, zero. It is so finely tuned that altering it by even one part in that astronomical number would make life impossible. This is the cosmological constant problem. Why is the energy of the void so infinitesimally small? One radical idea is that a perfect, unknown symmetry of nature forces the vacuum energy to be exactly zero. But then we are left to explain the tiny, non-zero value we detect. Another, even more mind-bending possibility is the multiverse. In this scenario, our universe is just one bubble in an infinite froth of universes, each with its own random value for the cosmological constant. We simply find ourselves in one of the exceptionally rare bubbles where the number is small enough to allow for galaxies and life to emerge. The value of this constant is not just a number. It is a dial on the universe. Turn it slightly, and reality as we know it vanishes. The fact that it is set to such a perfect, life-permitting value feels less like a coincidence and more like a signature, a direct pointer to a deeper principle that governs the very structure of spacetime. These slight but stubborn deviations in the decay of B mesons form a pattern of whispers growing into a coherent voice. For years, experiments like LHCb have been tracking a specific and exquisitely rare event. The moment a B meson disintegrates into a pair of lighter particles, such as two muons or an electron and its heavier cousin. According to the Standard Model, this process should be incredibly suppressed, happening only a handful of times out of billions of collisions. It is a delicate, unlikely dance dictated by the known forces. Yet, when physicists compile the data, they find these rare decays are happening just a little bit more often than the rules allow. The deviation is not enormous, but it is persistent, showing up across different experiments and in related decay channels. This is not one isolated anomaly, it is a family of them, all pointing in the same intriguing direction. They are known as flavor anomalies, and they challenge a fundamental principle: the idea that the laws of physics treat all three generations of particles equally. Why should a process involving second-generation muons be different from one involving first-generation electrons? The consistency of these hints suggests the presence of an unseen actor, a new particle mediating these decays behind the scenes. The prime suspects are exotic entities with names like leptoquarks, which can change a quark into a lepton, or a Z-prime boson, a heavier cousin of the known Z-boson. Either one would provide a new pathway for the decay, a secret tunnel that makes the forbidden process slightly more probable. If confirmed, this would be a direct citing of physics beyond the Standard Model, a force that specifically distinguishes between the families of matter. It would mean the universe has a richer, more textured set of rules for how particles transform, a hidden hierarchy governing the generations of matter. This pattern of rare events is like finding the same unusual symbol carved into different ancient ruins, a sign that a lost chapter of cosmic law is waiting to be read. That fragile balance in the vacuum energy confronts us with a cosmic fine-tuning, but our eighth pattern reveals a crack in what we thought was settled science. The mass of the W boson, a fundamental particle responsible for the weak nuclear force that powers the Sun, was believed to be known with absolute precision. For decades, its value was a cornerstone of the Standard Model, a number so critical that it interlocked with the masses of other particles like the Higgs and the top quark in an elegant, self-consistent web. Then, in 2022, the CDF collaboration at Fermilab announced a result that sent a shock through the physics community. After a painstaking analysis of a decade's worth of data, they reported the most precise measurement of the W boson's mass ever made. And it was wrong, not by a little, but by a statistically significant margin, heavier than the Standard Model prediction by an amount that cannot be explained by random chance. Imagine a master watchmaker crafting a perfect timepiece, where every gear and spring is calibrated to an exact specification. The W boson is one of those critical gears. Now imagine that, upon the most careful inspection with the finest tools, that gear is found to be microscopically thicker than the blueprint allows. The entire mechanism should, in theory, no longer keep perfect time. The implications are profound. The mass of the W boson is not an independent number. It is a calculated consequence of the Higgs mechanism and the strengths of other fundamental forces. A shift in its mass suggests that something is missing from our calculation. There could be unknown particles, lurking just beyond our detection, whose interactions subtly alter the Higgs field in a way that makes the W boson heavier. Or it could point to a flaw in our understanding of how electroweak symmetry breaks, the very process that gives these particles their mass in the first place. This anomaly is a stark reminder that no measurement, no matter how well established, is ever truly final. It demonstrates that the foundational framework of particle physics, while incredibly successful, may be resting on assumptions that are just slightly off. A single, stubborn data point can be the thread that, when pulled, begins to unravel our entire picture of the universe's inner workings. A stubborn disagreement over the speed of the cosmos itself forms our ninth pattern. We have two completely different ways of measuring how fast the universe is expanding, a number called the Hubble constant. One method looks back to the infant universe, studying the faint afterglow of the Big Bang known as the cosmic microwave background. This ancient light gives us a precise reading of the expansion rate from a time when the cosmos was just a hot, dense plasma. The other method measures the modern universe, observing the brilliant explosions of dying stars called supernova in nearby galaxies. Both techniques are incredibly sophisticated, the products of decades of painstaking work. Yet they refuse to agree. The early universe method gives one number. The local supernova method gives another, consistently higher, number. The gap between them is small but undeniable, and it has only grown more significant as our measurements have become more precise. This is the Hubble tension. It is as if you used two different clocks to time the same race. One clock, set at the starting pistol, says the runner should be at a certain point. But when you look, the runner is actually farther ahead, as if they had gotten a secret burst of speed somewhere along the way. The universe seems to be expanding faster now than our best models of its early history can account for. What could have given the cosmos this extra push? The most intriguing possibility lies in the realm of exotic particles. Perhaps a new form of energy, an early dark energy, briefly surged in the universe's adolescence, altering its expansion in a way that left a permanent mark. Or maybe unknown particles, relics from the first moments of time, subtly changed how matter and radiation interacted, throwing off our cosmic calculations. This tension is a profound bridge between the impossibly large and the infinitesimally small. It suggests that the behavior of particles we have not yet discovered is literally written into the fabric of space-time, dictating the fate of everything we see. The disagreement between our two clocks is not an error. It is a message, telling us that our story of the cosmos is missing a crucial chapter. A silent echo from the dawn of time carries our 10th clue. Long before the first stars ignited, the infant universe was a dark, expanding sea of hydrogen gas. This gas, however, was not completely uniform. It held a faint, specific signature, a whisper of radiation with a wavelength of 21 centimeters, born from the subtle flip of the hydrogen atom's electron. For years, cosmologists predicted exactly how this signal should appear to our telescopes. Then, the EDGES experiment, a simple array of radio antennas in the Australian outback, heard something strange. They detected the ancient absorption signal, but it was far deeper and more pronounced than any model had foreseen. This was not a minor discrepancy. It was as if the primordial hydrogen gas was significantly colder than it had any right to be. The standard story of cosmic dawn involves the first stars and galaxies slowly heating the gas around them with their ultraviolet light. But the EDGES signal suggests that something else was at work, a cosmic coolant that was chilling the hydrogen long before the stars turned on. The most thrilling possibility is that this mysterious coolant was dark matter itself. If dark matter particles, which vastly outnumber ordinary matter, interacted with the hydrogen gas through some unknown, non-gravitational force, they could have siphoned away its heat. This would be a revolution. For decades, we have only been able to infer dark matter's presence through its gravitational pull on galaxies. A direct interaction, a particle of dark matter bumping into a particle of ordinary matter and exchanging energy, has never been observed. The EDGES anomaly is a potential fingerprint of that very event, a fleeting touch from the hidden 95% of the universe's substance. It points to a dark sector teeming with its own particles and forces. a parallel reality that has been subtly influencing the evolution of the cosmos since its very first moments. This single, anomalous dip in a radio signal is a crack in the wall between our world and the dark world, a hint that the universe's greatest secret was hiding in the cold silence of its birth. Deep within the heart of our own galaxy, a silent beacon shines with a light we cannot see. The center of the Milky Way is a place of immense gravity and chaos, home to a supermassive black hole. But when we point our gamma-ray telescopes toward this maelstrom, they detect more than just the expected fury. They record a persistent, mysterious glow, an excess of high-energy gamma rays that spills out in a remarkably smooth and spherical halo from the galactic core. The simplest explanation would be a population of unseen pulsars, the spinning corpses of dead stars, which are known to emit gamma radiation. Yet the signal's distribution is wrong for that. Pulsars are point sources, and their gamma-ray emission would be clumpy and irregular, like individual lighthouses scattered across a dark sea. The signal we see is eerily uniform, a soft, diffuse fog of energy that blankets the entire central region. This smoothness is the key clue. It perfectly matches a prediction made by theorists decades ago. If dark matter is indeed a sea of invisible particles, and if those particles are their own antimatter counterparts, then whenever two of them collide, they should annihilate each other in a flash of pure energy, producing gamma rays. The dense core of the galaxy, where dark matter is predicted to be most concentrated, would be the perfect place for this annihilation to light up the darkness. This is not just a wild idea. Specific, well-motivated candidates for dark matter, like weakly interacting massive particles, or WIMP, naturally produce exactly this kind of smooth gamma-ray signature when they annihilate. The energy of the observed photons even lines up with the predicted mass range for these hypothetical particles. Of course, the case is not closed. The pulsar explanation is still plausible, and the debate among astrophysicists is fierce. But this galactic center excess remains one of the most compelling and direct hints that we might be on the verge of seeing dark matter not through its gravity, but through its own light. It suggests that the universe's dominant substance is not entirely inert. It may be interacting with itself according to a hidden set of rules, leaving behind a faint but detectable signature. The search to pinpoint the source of these gamma rays is a high-stakes treasure hunt, one that could finally reveal the particle nature of the cosmos' greatest mystery. This seemingly absolute rule is about to face its most stringent test. The transformation of a muon directly into an electron is a process so rare in our current understanding that it borders on the forbidden. Think of the particle families as separate, isolated islands. Electrons, muons, and tau particles are all leptons, but according to the standard model, a resident of one island should never be able to simply teleport to another. They can change identities through the ghostly dance of neutrinos, but a direct conversion, a muon turning into an electron with no neutrinos involved, is a violation of a sacred principle known as Lepton flavor conservation. The predicted rate for this event is almost zero, so small that it would take longer than the current age of the universe to observe it naturally. Yet, this is exactly what experiments like Mu-2e and COMET are designed to hunt for. They create intense beams of muons and fire them at atomic nuclei. The entire apparatus is a masterpiece of shielding, built to silence every other possible signal, listening with impossible sensitivity for the unique signature of a single electron born from a muon's direct transformation. Why would this be so revolutionary? Because it shatters a symmetry we have long taken for granted. It would mean that the differences between the electron, the muon, and the tau are not just arbitrary labels. There must be a deeper mechanism, a new force or a heavy intermediary particle, that actively treats these families differently, providing a secret bridge between the islands. Detecting this conversion would be like finding a law of nature that everyone believed was written in stone had actually been amended. It points directly to physics operating at energy scales far beyond the reach of any earthly collider. A fundamental restructuring of the rules that govern the very identity of matter. This delicate balance of existence, from the galactic core to the cosmic dawn, depends entirely on the stability of the stage itself. But what if that stage, the very vacuum of space, is fundamentally unstable? This is not science fiction, but a direct implication of our most precise calculations regarding the Higgs field. We have found that the universe might not be resting in its true, lowest energy state. Instead, it could be perched in a state of metastability, like a ball sitting precariously on the side of a hill rather than safely at the bottom of the valley. The hill is stable enough for now, but a sufficiently large nudge could send the ball rolling into the abyss. The pattern here is the precise mathematical shape of the Higgs potential, the landscape that defines its energy. Our measurements indicate this landscape has a peculiar form, one that leaves our vacuum balanced on a knife's edge. The terrifying implication is that a quantum fluctuation, a random tunnel through the energy barrier, could trigger a bubble of true vacuum to form somewhere in space. This bubble would then expand at the speed of light, rewriting the fundamental laws of physics as it goes. Atoms would disintegrate, forces would cease to function as they do now, and reality as we know it would be erased. The one comforting thought is that the predicted timescale for such an event is astronomically long, far exceeding the current age of the universe. But the very fact that it is even a possibility is deeply unsettling. Why is the cosmos set up in such a fragile way? This metastability is a powerful clue. It strongly suggests that our current understanding is incomplete, that there are particles or forces we have not yet discovered whose presence would naturally reshape the Higgs potential, creating a deep, stable valley for our universe to rest in. Supersymmetry is a prime candidate for providing this stability. The existence of superpartner particles would alter the equations, securing the vacuum and making our existence far less contingent on a cosmic accident. The fact that we live in a universe that appears metastable is not a death sentence. It is a signature, a mathematical cry for help, pointing toward the missing pieces that would make the cosmos truly stable and eternal. Our exploration of cosmic instability brings us to a profound silence, a nothingness that speaks volumes. The proton, the very anchor of the atom, appears to be immortal. This might sound like a good thing, a sign of cosmic permanence, but to a physicist, it is a deep and troubling mystery. Grand unified theories, or GUT, represent one of the most ambitious quests in science. They seek to show that the three non-gravitational forces, electromagnetism, and the weak and strong nuclear forces, are not separate at all. They are simply different facets of a single, primordial superforce that existed in the universe's first moments of unimaginable heat and density. These theories are mathematically beautiful and elegant, but they almost all carry a startling prediction. In a unified force, the fundamental identities of particles can blur. A quark, the building block of a proton, could potentially transform into a lepton, like an electron. This transformation would cause the proton to simply fall apart, to decay. The theories predict this decay should be incredibly rare, happening over timescales of 10 to the 34 years or more. That is a 1 followed by 34 zeros, a duration so long it makes the age of the universe seem like a single blink. But rare is not never. If protons decay, then all matter is ultimately temporary. The atoms that make up our bodies, our planet, and every star in the sky are living on borrowed time. To test this, scientists have built the most patient experiments in history. Deep underground, in mines shielded from cosmic rays, sit colossal tanks of ultra-pure water, like the Super Kamiok and Detector in Japan. These vessels are lined with incredibly sensitive light sensors, waiting to see the telltale flash of light that would be produced if a single proton inside one of the water molecules spontaneously decayed. They have waited for decades, monitoring more than 10 to the 34 proton years of exposure. The result is a profound and unexpected silence. Not a single confirmed proton decay event has ever been seen. This non-discovery is one of the most significant patterns in all of physics. The proton's stubborn stability is a massive constraint, a wall that many beautiful grand unified theories have smashed into. It tells us that any deeper theory of everything must include a powerful protective mechanism, a new symmetry or principle that explicitly forbids protons from decaying. This absence is a guidepost, forcing theorists to build more sophisticated models that can achieve the grand dream of unification while simultaneously guaranteeing the longevity of the atomic world. The fact that the proton does not decay is not a boring confirmation of the status quo. It is a loud, clear message from the universe about what a truly fundamental order must look like. An order that protects the very building blocks of our reality. That profound silence from the proton's stability points to a universe governed by remarkably precise rules. Yet another pattern reveals a different kind of precision, one so exact it feels like a cosmic oversight. The strong nuclear force, which glues quarks together inside protons and neutrons, is described by a theory called quantum chromodynamics. This theory is a masterpiece of mathematical consistency, but it contains a tiny, hidden flaw. The equations allow for a parameter, a single number known as theta, that should violate a fundamental symmetry of nature. This symmetry, called CP, is the combination of charge and parity, essentially the idea that the laws of physics should work the same for a particle and its mirror image antimatter counterpart. If theta were anything other than zero, it would leave a subtle but detectable scar on the neutron, one of the building blocks of every atomic nucleus. It would give the neutron a slight internal imbalance of electric charge, creating what is known as an electric dipole moment. Think of the neutron as a perfect sphere. A non-zero theta would distort that sphere, making it ever so slightly egg-shaped, with a positive charge shifted toward one end and a negative charge toward the other. This would be a monumental discovery, a clear sign of asymmetry in the heart of matter itself. So physicists have built exquisitely sensitive experiments to measure the shape of the neutron. They suspend ultra-cold neutrons in magnetic traps and probe them with extreme precision. The result is not a small number. It is a resounding zero. The neutron is, to the best of our ability to measure, a perfectly symmetrical sphere. The theta parameter is not just small. It is less than a billionth of a billionth of a billionth. This incredible fine-tuning is the strong CP problem. Why is this number so unnaturally close to zero? The theory allows it to be any value, yet the universe has chosen a value of such perfect symmetry that it seems like a miracle. It is as if a safe with a dial containing 10 billion possible combinations was found already open, set precisely to the one combination that leaves no trace. The most elegant solution to this puzzle is the proposal of a new symmetry, named the Peck-Quinn symmetry. This idea introduces a new field that permeates all of space. In the early, hot universe, this field would have dynamically adjusted itself, automatically forcing the theta parameter to zero, erasing the asymmetry as the cosmos cooled. The fascinating consequence of this mechanism is the prediction of a new particle, the action. This hypothetical particle would be incredibly light and barely interact with normal matter, making it a perfect candidate for the mysterious substance we call dark matter. The strong CP problem, therefore, is not an isolated curiosity. It is a direct bridge. It connects the tiny world of the neutron to the vast, dark halos of galaxies. It suggests that the puzzling symmetry of the strong force and the invisible grip of dark matter might be two sides of the same coin, unified by a hidden principle that cleansed the universe of a fundamental imperfection at its birth. The pristine chemistry of the universe's first stars holds a stubborn contradiction. When we peer back to the very first minutes after the Big Bang, our models of this fiery dawn, known as Big Bang nucleosynthesis, are spectacularly successful. They predict with stunning accuracy the cosmic abundances of the lightest elements, hydrogen and helium, that would have forged in that initial inferno. The numbers we calculate match almost perfectly what we observe in the oldest stars, the celestial fossils that formed from unpolluted primordial gas. This success gives us immense confidence in our basic picture of the universe's hot beginning. But there is one glaring exception. The model predicts that a specific isotope, lithium-7, should have been created in a certain amount. Yet when astronomers measure the lithium content in these ancient stars, the value is consistently off by a factor of about 3. There is 3 times less lithium in the universe than there should be. This is not a small observational error. It is a persistent, glaring mismatch known as the cosmological lithium problem. Where did the lithium go? One possibility is that our understanding of nuclear physics in those extreme conditions is incomplete. Perhaps a key reaction rate involving beryllium or other light nuclei is slightly different than we have measured in our laboratories. But after decades of checking and rechecking, no conventional nuclear solution has emerged. This opens the door to a far more thrilling explanation. What if the discrepancy is not a flaw in our nuclear physics, but a clue to new particle physics? In the frantic first minutes, the universe was a seething plasma of energy and particles. If unknown, lightweight particles were present, they could have subtly altered the energy density of the cosmos, changing the rate at which it expanded and cooled. Even a minuscule change in the expansion rate during this critical window would have shifted the delicate balance of nuclear reactions, effectively turning down the dial on lithium production. Alternatively, these new particles could have decayed, injecting just enough extra energy to break apart the fragile lithium nuclei as they were forming. The lithium problem connects the grand scale of cosmology directly to the quantum realm. It suggests that the chemical signature of the oldest stars is a cosmic fingerprint, preserving the trace of a particle that has otherwise vanished from the universe. The missing lithium is a message from the first 3 minutes, a silent witness to physics operating at energies we can never recreate, waiting for us to decipher its code. The sheer mass of the top quark makes it a unique window into the quantum world. While other quarks are instantly bound into composite particles like protons, the top quark is so heavy and unstable that it decays almost the moment it is created. It never gets a chance to dress itself in the cloud of other particles that typically obscures a quark's true nature. This gives us an unparalleled opportunity to observe a bare quark in action, a direct look at a fundamental ingredient of matter. But this pristine view comes with a mystery. When physicists at the Large Hadron Collider meticulously reconstruct these fleeting events, tracing the paths and energies of every particle that sprays out from a top quark's demise, they sometimes find a subtle mismatch. The energy distribution among the decay products, the specific way momentum is shared out, does not always align perfectly with the incredibly detailed computer simulations based on the standard model. The deviations are small, buried in mountains of data, but they are persistent. It is as if we have the blueprint for a perfectly balanced explosion, yet in a handful of cases, the debris flies out with just a little more or a little less energy in a certain direction than the blueprint predicts. What could be nudging these decays off their expected course? The leading suspect is an unseen particle meddling in the process. A prime candidate is a charged Higgs boson, a heavier relative of the famous Higgs that would open up a new, forbidden decay path for the top quark. The presence of such a particle would slightly alter the kinematics, the energy ballet of the decay, leaving behind this faint statistical signature. This is not a dramatic crash, but a barely perceptible shift in the rhythm, a pattern of whispers in the data that suggests the top quark, the ultimate heavyweight of the particle world, is sensitive to forces and particles that lie just beyond our current horizon. A shadow briefly fell across the data, a ghost that captured the imagination of the entire physics community for one thrilling year. In 2015, the two giant detectors at the Large Hadron Collider, ATLAS and CMS, independently saw the same faint signal. It appeared as a tiny bump on a graph, a small excess of events where 2 photons of light were produced with a combined energy of 750 giga-electron-volts. In the world of particle hunting, a pair of photons is a pristine signature. They are the clean, direct fingerprints of a new particle's demise. Unlike messy decays that produce a cascade of hadrons, a diphoton resonance is a clear, unmistakable signal. For a moment, it seemed as if we had stumbled upon something monumental, a heavy particle not predicted by the standard model, perhaps a heavier cousin of the Higgs boson or even a graviton, the hypothetical carrier of gravity. The excitement was palpable because this was exactly the kind of pattern the collider was built to find. But then, as more data was collected in 2016, the bump began to fade. The extra events, which had seemed so promising, slowly melted back into the background noise of random collisions. The 750 GeV resonance was not a discovery. It was a fluctuation, a statistical mirage. Yet, its brief appearance was far from a failure. It was a masterclass in the scientific process. It showed how a potential pattern is identified, scrutinized, and ultimately validated or dismissed. The entire episode highlighted the delicate balance between hope and rigor, reminding us that discovery requires not just a signal, but a signal that grows stronger with more light, not one that retreats into the shadows. The resonance may have vanished, but it left behind a valuable lesson about the energy scales we are probing and the tantalizing possibility that we are brushing against the edges of where new physics must lie. High above the frozen expanse of Antarctica, a balloon the size of a football stadium drifted silently in the thin, cold air. Suspended beneath it was an experiment named Anita, a sophisticated array of radio antennas listening not for sound, but for the faint whispers of the universe's most elusive particles. Its mission was to detect the ghostly signatures of high-energy neutrinos crashing into the ice sheet below. Most of the signals it picked up were exactly what physicists expected. But 2 events, separated by years, were so bizarre they defied all logical explanation. Anita heard the distinct radio crackle of a high-energy particle. But it was coming from the wrong direction. Instead of striking the ice from above, these particles appeared to be emerging from deep within the Earth itself. This is not just unusual, it is supposed to be impossible. According to the standard model, a neutrino with that much energy would be completely absorbed by the thousands of miles of solid rock it would have to travel through. It would be like a bullet trying to pass through an entire mountain. These anomalous upward-going events are more than just glitches. They are profound outliers that challenge our most basic assumptions about how particles interact with matter. If these were standard model neutrinos, they should not exist. So what did Anita actually detect? The most thrilling possibility is that these were not ordinary neutrinos at all, but something far more exotic. One candidate is the sterile neutrino, a hypothetical particle that, as its name implies, is utterly aloof. It would feel none of the fundamental forces except gravity, allowing it to pass through the entire planet as if it were not even there. Another idea from supersymmetry suggests a particle called the STAU, a heavier, slower decaying cousin of the tau lepton. A STAU could be produced by a cosmic ray collision in the atmosphere on the opposite side of the Earth, then travel through the planet at nearly the speed of light, decaying just as it emerges near Antarctica and creating the signal Anita observed. Either explanation points to the same astonishing conclusion, that we are witnessing the faint signature of a hidden sector of reality, a realm of particles that barely acknowledge our own. These two mysterious events are like footprints in the snow, left by a creature that passed through a solid wall. They are a direct challenge, suggesting that the universe is populated with phantoms that move through our world without leaving a trace, their presence revealed only by the most improbable and fleeting of encounters. Deep underground, within a vat of liquid xenon so pure it acts as its own universe, a search for the ultimate ghost was underway. The Xenon 1T experiment was designed to feel the faintest of whispers, the gentle nudge of a dark matter particle colliding with a xenon atom. For years, it listened in profound silence. Then, in its final analysis, it caught something. Not the clear signal of dark matter, but a faint, unexpected hum at the very lowest energies, a slight excess of events that should not have been there. This was not a shout of discovery, but a perplexing murmur. The immediate, mundane explanation was contamination. A tiny, almost undetectable amount of a radioactive isotope called tritium could have seeped into the xenon, its decay perfectly mimicking the signal they were hunting. It is the constant challenge of these ultra-sensitive experiments, a battle against the faintest background noise from the ordinary world. But the pattern of this excess was tantalizing. It also matched with uncanny precision the predicted signal for two entirely new physics phenomena. One possibility was solar actions, the very particles proposed to solve the strong CP problem, streaming out from the heart of our Sun. Another was a new property of neutrinos, a surprisingly large magnetic moment that would allow these phantoms to interact with electrons in a way the standard model forbids. This ambiguity is the essence of the pattern. The Xenon 1T excess is a masterclass in how the frontier of physics has evolved. Our detectors have become so exquisitely sensitive that they are no longer just hunters of one specific prey. They are microphones listening to the quantum vacuum itself, and they can pick up the faint echoes of many different new phenomena. The signal could be one thing or the other, or even something no one has yet considered. The lesson is that nature does not always present us with clean, isolated clues. It often gives us a tangled knot of possibilities, and the work of science is to patiently unpick each thread, testing one explanation against another until the true source of the whisper is revealed. This single, ambiguous signal from a tank of liquid xenon is a powerful reminder that the path to a deeper order is rarely a straight line, but a maze of fascinating, interconnected mysteries. This delicate balance of forces and particles rests on a set of fundamental numbers, parameters that seem to be fixed by nature itself. One of these is the Cabibbo angle, a crucial but obscure value that dictates the probability with which quarks change their identity during radioactive decay. Think of it as the precise angle of a ramp that connects the world of up and down quarks to the world of strange and charm quarks. It is a single number that should be perfectly consistent across all measurements. For decades, it appeared to be exactly that, a stable pillar in the mathematical architecture of the standard model. But as our experiments have grown more precise, a tiny crack has appeared in this pillar. When physicists measure the Cabibbo angle using the decay of particles called kaons, they get one value. When they measure it using the decays of other particles, like neutrons or certain mesons, they get a slightly different value. The mismatch is minuscule, a fraction of a percent, but it is statistically significant and stubbornly persistent. This is the Cabibbo angle anomaly, and it points to a violation of a sacred principle known as unitarity. In essence, unitarity is the requirement that all probabilities must add up to 100%. If the angles describing the connections between quark families do not perfectly align, it means the math does not close. The probabilities do not sum correctly, suggesting that something is missing from the equation. This subtle mismatch is like finding that a master key, designed to open 3 specific locks, fits each one just a little bit imperfectly. The most exciting explanation is that there are more locks than we thought. Perhaps the 3 familiar generations of quarks are not the whole story. There could be a fourth, much heavier generation, lurking just beyond our detection. The presence of these hidden quarks would subtly warp the mixing angles, causing the small but measurable discrepancy we see. Alternatively, a new force, carried by a Z-prime boson, could be interfering with the decay processes, selectively altering the rates and throwing off our measurement of this fundamental angle. Either way, this anomaly is not a flaw in our measurements, but a flaw in our map. It suggests that the simple, three-generation picture of matter is incomplete, and that the true family of particles is larger and more complex than we ever imagined. A different kind of signal whispers from the dark heart of galaxy clusters. Across the universe, immense clouds of hot gas, trapped by the gravity of unseen dark matter, glow with the fierce light of X-rays. When astronomers point their most powerful space-based telescopes at these colossal structures, they see a familiar forest of spectral lines, each one the fingerprint of a known chemical element like iron or potassium. But nestled among these expected signatures is a faint, persistent ghost. At a very specific energy, 3.5 kilo-electron volts, there is a tiny, unexplained spike of X-ray light. It appears in the Perseus cluster, in the center of the Milky Way, and even from our neighboring Andromeda galaxy. This is not the signature of any atom we have ever seen. It is an anomaly that cuts through the cosmic noise, a consistent, monochromatic note played on an instrument we cannot see. The most thrilling explanation for this mysterious line is the death of a particle. Specifically, it could be the signature of a sterile neutrino, a hypothetical dark matter candidate, decaying into an ordinary photon and another, lighter neutrino. In this scenario, the sterile neutrino is its own antiparticle. When two of them meet, they annihilate, and part of their mass is converted directly into a flash of X-ray light with the exact energy we observe. The 3.5 keV line would then be the death rattle of dark matter itself. Think of it as a cosmic bat signal. For decades, we have only been able to map dark matter through its gravitational shadow. This X-ray line is the first potential glimpse of its true substance. A direct message from the 95% of the universe that has, until now, remained utterly silent. Confirming this signal would be a revolution. It would transform dark matter from a mathematical abstraction into a tangible particle with a specific mass and a specific way of interacting. It would give us a concrete target, a known piece of the puzzle to fit into a deeper, more complete theory of everything. The hunt to verify this faint X-ray glow is now one of the most urgent quests in astrophysics, a search for the spectral signature of the invisible universe. The electron's magnetic personality is a marvel of cosmic engineering. While its heavier cousin, the muon, wobbles with a tantalizing anomaly, the electron itself behaves with an almost supernatural obedience to our predictions. This obedience is captured in a number called the G factor, a value that describes the strength of its magnetic field. According to our most trusted theory, quantum electrodynamics or QED, this number should be almost, but not quite, 2. The decimal places that follow are a testament to one of humanity's greatest intellectual achievements. For decades, theoretical physicists have performed calculations of staggering complexity, accounting for the electron's interactions with the ghostly particles of the quantum vacuum. They have drawn thousands of intricate Feynman diagrams, each representing a possible way the electron can momentarily emit and reabsorb virtual photons or even particle-antiparticle pairs. The result is a theoretical prediction for the electron's magnetic moment that is precise to 1 part in a trillion. It is like predicting the exact circumference of the Earth to within the width of a single human hair. And when experimentalists trap single electrons in exquisitely crafted magnetic bottles called penning traps, cooling them to near absolute zero and measuring their subtle spin, the results match this prediction with breathtaking accuracy. This is not just a confirmation, It is a lockstep agreement between human calculation and natural law. Yet, within this perfect agreement lies a profound pattern. The very fact that QED works so flawlessly, that no deviation can be found even at this unbelievable level of precision, is itself a powerful clue. It acts as a severe constraint, a cosmic bouncer that forbids many speculative theories from entering the club of reality. Any proposed new particle or force must be gentle enough, or hidden enough, that it does not disturb this perfect magnetic balance. Pushing this measurement to even greater precision is like tightening a screw on the foundation of physics. The more perfect the agreement becomes, the smaller the crack must be for a deeper order to reveal itself. We are essentially searching for a flaw in a perfect diamond, knowing that the slightest, most infinitesimal scratch would point to something entirely new shining beneath the surface. This overwhelming preference for matter is not just an experimental quirk. It is the defining feature of our existence. Every galaxy, every star, and every atom in our bodies is a testament to a cosmic victory won in the universe's first fleeting moments. The question of why there is something rather than nothing finds its answer here, in a process called baryogenesis. The Standard Model does possess a mechanism to create this imbalance, a tiny crack in the perfect mirror between matter and antimatter known as CP violation. But the effect is pathetically weak, like a single drop of water trying to fill an ocean. It can only produce a surplus of about 1 part in a billion, a mere sprinkle of matter left over after the Great Annihilation. Yet, to build the cosmos we see, that initial asymmetry had to be enormous. Something far more powerful must have intervened, a process that aggressively favored the creation of matter on a colossal scale. This requires 3 essential ingredients, conditions far more dramatic than anything in our current textbooks. There must be a process that violates the conservation of baryon number, meaning it can actually create more matter than antimatter from pure energy. There must be a profound violation of both charge and parity symmetry, a fundamental lopsidedness in the laws of physics themselves. And crucially, this entire event must have occurred out of thermal equilibrium, a sudden, violent departure from the smooth, hot soup of the early universe. Think of it as a cosmic phase transition, like water suddenly flash freezing into ice. In that rapid shift, the rules can change, creating pockets where matter is dramatically favored. The most compelling ideas point to physics at almost unimaginable energies. Heavy, right-handed neutrinos, far more massive than any particle we know, could have decayed asymmetrically in the early universe, their slight bias seeding the entire material world. Or perhaps the event was tied to the grand unification of forces, when the strong, weak, and electromagnetic forces were one, a realm where protons themselves are unstable. The very fact that we live in a universe made of stuff is the ultimate pattern, a clue written across the entire sky. It is a silent, continuous reminder that the rules we have uncovered are merely the opening chapter of a much grander story, one that explains the most important fact of all, our own presence here to observe it. But the question of our existence rests on a paradox that strikes at the very nature of reality itself. Imagine the ultimate vault, a black hole, from which, according to Einstein's general relativity, nothing, not even light, can ever escape. Now throw a book into it. That book is made of atoms which are made of particles, and those particles contain information, the specific arrangement of quantum states that define that book. According to the classical view of black holes, that information is gone forever, locked behind the event horizon. It has vanished from our universe. But quantum mechanics, the other pillar of modern physics, holds a sacred and unbreakable law. Information can never be truly destroyed. It can be scrambled, it can be hidden, but it must, in principle, be recoverable. You cannot burn a book and lose its story forever. The information is just transformed into the heat and light of the fire. This is the black hole information paradox, a direct and violent clash between our 2 most successful theories of reality. For decades, Stephen Hawking seemed to seal the case for destruction. He showed that black holes are not entirely black. They slowly evaporate by emitting a faint glow of radiation. But Hawking radiation is purely thermal. It is random noise, carrying no information about what fell in. So when the black hole finally evaporates completely, all the information about the book, the particles, everything, appears to be irretrievably lost. This is the paradox in its starkest form. The pattern here is not a single experimental data point, but a roaring theoretical silence, a fundamental inconsistency in the bedrock of physics. Resolving it demands a revolution. One radical idea is the firewall proposal. What if the event horizon is not a smooth, uneventful boundary, but a searing wall of high-energy particles? Anything crossing it would be instantly incinerated, preserving information at the boundary but violating the gentle space-time curvature predicted by Einstein. Another, even more profound idea is holography. This suggests that all the information contained within the three-dimensional volume of a black hole is actually encoded on its two-dimensional surface, its event horizon like a cosmic DVD. The three-dimensional world we experience, including the particles that made the book, might itself be a projection from a two-dimensional reality. The information never falls in, it is just smeared across the horizon, waiting to be slowly released as the black hole evaporates. This paradox forces us to confront the idea that particles and spacetime are not separate entities. They must emerge from a more fundamental structure, a theory of quantum gravity where the very concepts of location and information are rewritten. The black hole is not just a cosmic vacuum cleaner. It is the ultimate laboratory, testing the limits of our understanding and pointing toward a deeper order where the fate of a single particle is tied to the fate of the cosmos. Floating 250 miles above the Earth, attached to the backbone of the International Space Station, a machine the size of a delivery van silently sifts through the rain of the cosmos. The alpha magnetic spectrometer is not a telescope in the traditional sense. It is a cosmic fingerprint scanner, designed to identify and count the individual particles that scream across space at nearly the speed of light. For over a decade, it has been meticulously cataloging this cosmic ray traffic, and it has found something strange happening with a specific type of passenger, the antimatter counterpart of the electron, known as the positron. According to our standard astrophysical models, the number of these high-energy positrons should steadily decrease as their energy increases, but the data from the spectrometer tells a different story. The positron fraction, the ratio of positrons to all electrons, does not fall off. It actually rises. This is the AMS02 positron excess, a clear and persistent pattern written in the high-energy radiation bathing our solar system. Where are these unexpected antimatter particles coming from? The most conventional explanation points to cosmic lighthouses called pulsars. These rapidly spinning, magnetized cores of dead stars can accelerate particles to tremendous energies, potentially creating electron-positron pairs that flood into space. Yet, the smooth, featureless rise in the positron fraction observed by the spectrometer is a difficult profile for known pulsars to produce. Their signals tend to be more specific, more like sharp peaks on a graph. The smoothness of the curve is what makes the dark matter explanation so compelling. If dark matter is made of particles that are their own antimatter, then whenever two of them collide, they could annihilate each other in a flash of energy, producing a spray of familiar particles, including a steady stream of positrons. The energy of those positrons would depend directly on the mass of the dark matter particle. The beautiful fit between the observed rise and the predictions of certain theoretical models is like finding a key that slides smoothly into a lock we have not yet opened. This is not a direct detection of dark matter, but it is a powerful indirect signal. It suggests that the mysterious substance that holds galaxies together might also be quietly destroying itself in the halo of our own Milky Way, and we are sitting in the fallout. The positron excess turns the entire galaxy into a laboratory, hinting that the answers to particle physics might not only lie in underground caverns or colossal colliders, but are raining down upon us from the void between the stars. Even the most stable components of matter can hide profound mysteries. Inside every atomic nucleus, the neutron is a cornerstone of our material world, seemingly inert and permanent. But when freed from the nucleus, it becomes fragile, living for only about 15 minutes before it decays. This lifetime is a fundamental number, a critical parameter that must be measured with ultimate precision. Yet, there is a troubling crack in this seemingly solid measurement. Two of the most advanced experiments, using completely different methods, cannot agree on exactly how long a free neutron lives. One approach traps ultra-cold neutrons in a magnetic bottle, a physical container where scientists can literally count the number of neutrons that disappear over time. The other method creates a beam of neutrons and meticulously counts the protons that are produced as the neutrons decay. In principle, these two results should be identical. But they are not. The bottle method suggests a slightly longer lifetime than the beam method. The difference is less than 10 seconds, a tiny gap in a span of nearly 900 seconds, but it is a gap that has persisted for years, stubbornly defying explanation. This is not an experimental error. It is a genuine discrepancy, a pattern that whispers of an unseen process. The most thrilling possibility is that we are not counting all the ways a neutron can die. Perhaps on very rare occasions, a neutron does not decay into a proton, an electron, and an antineutrino as the standard model dictates. Instead, it might transform into something invisible, something that slips through our detectors entirely. It could be decaying into a particle of dark matter. Imagine a sealed room with a single door. You count how many people leave through the door, and you also count how many people remain inside over time. If the two numbers do not match, you are forced to conclude there must be a secret passageway out of the room. The neutron lifetime discrepancy is precisely that clue, pointing to a hidden exit from the world of ordinary matter into the dark sector. This would be a connection more direct than any gravitational inference, a fundamental decay process that literally turns the building blocks of our world into the unseen substance that shapes the cosmos. The humble neutron, a particle we have known for a century, may be the very messenger that finally reveals the true nature of dark matter. The silent stability of the neutron's lifetime gives way to a cosmic event that tested the very fabric of spacetime. In February 1987, light from a dying star reached Earth, a supernova explosion in the Large Magellanic Cloud that was visible to the naked eye. But hours before that light arrived, a different kind of messenger slipped through our planet. Deep underground in Japan, the Kamiok and IMB detectors registered a brief, unmistakable burst of 24 neutrinos. These ghostly particles had traveled 160,000 light-years, and they all arrived within a window of just a few hours. This might seem like a long time, but for physics, it was a stunningly tight grouping. The neutrinos, despite having a tiny amount of mass, appeared to have all raced through space at essentially the same speed, the speed of light. This observation places a profound constraint on our theories. Some of the most speculative ideas in physics, particularly models of quantum gravity that try to merge Einstein's relativity with quantum mechanics, predict that spacetime itself might have a subtle, grainy texture at the smallest scales. If this is true, then the speed of a particle could depend on its energy. Higher energy particles might feel this graininess more, traveling at slightly different speeds than their lower energy counterparts. Over a cosmic distance of 160,000 years, this effect would have been dramatically amplified. The burst of neutrinos from the supernova, which spanned a range of energies, should have stretched out into a signal lasting for many months, even years. The highest energy neutrinos would have arrived first, followed by a long, slow trickle of the slower ones, but that is not what happened. They came in a single, sharp pulse. This is a pattern defined by its absence, a non-pattern that speaks volumes. The flight time anomaly that did not happen tells us that Lorentz invariance, the cornerstone of Einstein's theory that states the laws of physics are the same for all observers, appears to hold firm even over these immense distances. It forces the most radical theories of quantum gravity to conform, ruling out those that violate this fundamental symmetry. The ghostly pulse from a stellar death acts as a cosmic referee, whispering that any deeper order we discover must respect the universal speed limit that has guided our understanding for over a century. The search for cosmic symmetry leads to a fundamental question about the very nature of magnetism. Every magnet you have ever held, from a simple refrigerator magnet to the Earth itself, is a dipole with an inseparable north and south pole. Break a bar magnet in half, and you do not get isolated poles. Instead, you create two new, smaller dipoles, each with its own north and south. This is one of the most enduring rules of nature, seemingly written into the fabric of electromagnetism. Yet, many of our most ambitious theories insist this should not be the case. Grand unified theories, which dream of merging the fundamental forces, almost universally predict the existence of magnetic monopoles, solitary north or south poles wandering the cosmos like elemental ghosts. These would be massive, stable particles, cosmic relics left over from the universe's first moments of unimaginable heat, when the forces were one. Their predicted properties are staggering. A single magnetic monopole would carry a magnetic charge so profound it would be like a fundamental unit of magnetism, a quantized anchor point. So where are they? Despite decades of ingenious searches, from deep underground laboratories to experiments carried on high-altitude balloons, not a single confirmed magnetic monopole has ever been found. Their absence is not a quiet failure. It is a deafening silence, a pattern defined by what is missing. This non-discovery is as informative as any detection. It tells us something crucial about the history of our cosmos. The most compelling explanation is cosmic inflation, the idea that the universe underwent a period of hyper-accelerated expansion in its first fraction of a second. This inflationary burst would have stretched spacetime so dramatically that any primordial monopoles produced would have been diluted to an almost infinitesimal density, effectively scattering them so far apart that the chance of one ever passing through our detectors is virtually zero. Their absence, therefore, becomes a powerful piece of evidence for inflation itself. Alternatively, their non-appearance could mean our theories about grand unification are subtly wrong, that the phase transitions in the early universe unfolded in a way that did not produce these exotic objects. Either way, the empty-handed search for monopoles is a critical guidepost. It forces any deeper, more unified order to include a mechanism that explains this profound emptiness, a reason why the universe prefers its magnetic poles forever bound together. This cosmic preference for bound magnetic poles is mirrored by a critical transition in the universe's own infancy. The very moment the Higgs field settled into its current value was not a gentle fade, but a cosmic event of staggering consequence. Our best model describes it as a smooth crossover, a gradual shift like butter softening on a warm day. Yet, to explain the overwhelming existence of matter, we seem to need something far more violent. The process of baryogenesis, the genesis of matter's dominance, often requires a shock to the system. A strong first-order phase transition would provide exactly that. Picture a pot of water coming to a rolling boil. Bubbles of a new phase of steam suddenly form and rapidly expand, colliding and releasing immense energy. In the early universe, such bubbles would be pockets where the Higgs field had already acquired its new value. expanding through a sea of the old, high-energy state. This turbulent, out-of-equilibrium environment is the perfect crucible for creating a permanent matter-antimatter asymmetry. The violent collisions of these bubble walls could have provided the necessary conditions to satisfy all three requirements for baryogenesis in one dramatic event. The smooth crossover predicted by the Standard Model is too gentle, too orderly. It lacks the necessary punch to create the cosmic imbalance we see today. This mismatch is a profound clue written into the thermal history of everything. It tells us that our understanding of the Higgs field's awakening is incomplete. There must be new physics, additional fields or particles that interacted with the Higgs in those first moments, making the transition sharp and explosive. The hidden order we seek must therefore be a dynamic one, capable of orchestrating the universe's most critical moments of change. It is not just a set of static rules, but a narrative of transformation, where the fate of every atom was decided by the ferocity of a transition we have only just begun to understand. The line between the quantum weirdness and our familiar reality is not a wall, but a fading gradient. For decades, we accepted a simple division, a world where the bizarre rules of superposition and entanglement applied only to the smallest particles, like electrons and photons. But that boundary is now crumbling. In laboratories around the world, scientists are performing experiments that would have seemed like pure fantasy just a generation ago. They are taking molecules composed of thousands of atoms, structures large enough to be seen with powerful microscopes, and placing them into a state of quantum superposition. This means a single molecule is made to exist in two places at the same time. It is not split in half, but the entire complex structure, with all its intricate atomic bonds, is delocalized, its position spread out like a ghostly cloud until it is measured. This is no longer the realm of the infinitesimal. These molecules are approaching the scale of tiny life forms like viruses. The pattern here is not a sudden cutoff, but a gradual fading of quantum effects as mass and complexity increase. It is as if the quantum world is not a separate domain, but the underlying layer of all reality, a layer whose strange features simply become harder to detect as objects grow larger, not because the rules change, but because they are drowned out. This challenges one of the oldest interpretations of quantum mechanics, the idea that a conscious observer or the act of measurement causes the wave function to collapse, forcing a particle to choose a single state. If a molecule of 2,000 atoms can be in two places at once, what constitutes a measurement? Is there a special size where consciousness is required? The smooth transition suggests a different answer. It hints that something else is at work, a physical process that gradually suppresses quantum coherence. One compelling idea involves gravity. At tiny scales, gravity is negligible, but as an object's mass increases, its own gravitational field might somehow pin it down to a single location, acting as a continuous natural measurement. Other theories propose spontaneous collapse models, where the wave function has a tiny, inherent probability of collapsing on its own, a probability that becomes significant only for large collections of particles. Each successful experiment with a larger molecule is not just a technical triumph. It is a direct probe into the mechanism that builds our orderly, classical world from the chaotic quantum foundation. We are witnessing the very process by which certainty emerges from probability, watching as the ghostly whisper of superposition is slowly silenced by the growing weight of reality itself. Einstein's deep unease with the probabilistic nature of quantum mechanics found its sharpest focus in a thought experiment he devised with his colleagues Podolsky and Rosen. They aimed to prove that the theory was incomplete, that particles must possess hidden properties determining their fate from the moment of their creation. This became known as the EPR paradox, a challenge that seemed to expose a fatal flaw. If two particles are born together and then fly apart to opposite sides of the galaxy, quantum mechanics insists they remain linked or entangled. Measuring one would instantly determine the state of the other, no matter the vast distance separating them. To Einstein, this spooky action at a distance was absurd, a violation of the cosmic speed limit set by light. He was convinced a deeper, local reality existed, where information could not travel faster than light, and particles carried their own independent instructions. For decades, this remained a philosophical debate, a battle of interpretations fought on paper. Then, a physicist named John Bell found a way to translate the argument into mathematics. He devised a set of inequalities, a precise test. If Einstein was right and hidden variables guided the particles, then certain statistical correlations in their measurements would never exceed a specific limit. If quantum mechanics was correct, those limits would be shattered. Building an experiment to test Bell's theorem required near-impossible levels of precision to close every possible loophole where hidden information could sneak through. Over years, with ever more sophisticated setups, physicists sent entangled photons through long fibers, used random number generators to choose measurement settings at the last possible instant, and placed detectors so far apart that no light-speed signal could possibly coordinate the results. The outcome was definitive and, to many, unsettling. The inequalities were violated again and again. The particles were correlated in ways that no local, hidden variable theory could ever explain. Spooky action was not a philosophical curiosity, it was a feature of the world. This pattern of entanglement is now one of the most rigorously tested facts in all of science. It tells us that the universe is fundamentally non-local, that at its deepest level, reality is interconnected in a way that defies our classical intuition of separate, isolated objects. The two particles, even across a galactic void, do not behave as individuals. They behave as a single system. This is a profound clue, a direct signal from the quantum fabric that any deeper theory must embrace, not explain away. It suggests that the separateness we experience in our everyday lives is a kind of illusion, an emergent property of a world built upon a far more holistic and deeply woven foundation. The challenge for a theory of everything is not to erase this spookiness, but to build a framework where such intimate connection is the natural, starting state of existence. The profound interconnectedness revealed by entanglement hints at a universe far more unified than it appears. But what if that unity comes at the cost of an even more radical idea, that our experience of space itself is an illusion? This brings us to a pattern not found in a detector, but etched into the theoretical fabric of reality, the holographic principle. It begins with a strange fact about black holes. Stephen Hawking taught us that a black hole has entropy, a measure of its hidden information or disorder. But the value of this entropy is not proportional to the black hole's volume, as you might expect for a three-dimensional object. Instead, it is precisely proportional to the surface area of its event horizon. It is as if all the information about everything that ever fell into the black hole, every star, every planet, every book, is not stored within its vast interior, but is smeared like a cosmic code onto its two-dimensional surface. The holographic principle takes this black hole thermodynamics and proposes that it is not a special case. It is a universal law. The principle states that all the information needed to describe a volume of space can be encoded on its lower dimensional boundary. A three-dimensional room, with all its furniture and light and air molecules, could be completely described by the information painted on its walls. This is a staggering reduction. It suggests that the true, fundamental degrees of freedom of the universe, the most basic units of reality, are not the particles we see moving in three dimensions. They are something else, something simpler, living on a distant, two-dimensional surface at the edge of the cosmos. Our rich, three-dimensional reality, with its depth and texture, would then be a projection, a hologram generated from this simpler, lower-dimensional reality. Think of it like watching a three-dimensional movie. The experience seems fully immersive, but all the information needed to create that illusion is contained on a flat, two-dimensional screen. The holographic principle suggests our universe operates on a similar, albeit far more profound, principle. This is a pattern of breathtaking theoretical elegance. It hints that the apparent complexity of our world, with its countless particles and forces, is a kind of redundancy. The true laws of physics might be vastly simpler and more compact, written in a two-dimensional language we have not yet learned to read. The challenge for us is that we are living inside the projection. We are the characters in the movie, trying to figure out the nature of the screen by studying the shadows on the cave wall. If this principle is correct, then the search for a unified theory is not about finding new particles in our three-dimensional world. It is about cracking the code on the cosmic boundary, learning to read the universe's original, two-dimensional script. This intricate dance of constants is not a random drift, but a precise mathematical journey. Hidden within the equations of quantum field theory is a mechanism called the renormalization group. It is the universe's own zoom function. Imagine looking at a coastline from space. It has a certain rugged shape. As you fly closer, you see more detail, more inlets and peninsulas. The renormalization group is the mathematical tool that tells you exactly how your description of that coastline must change as you change your perspective, from a satellite view down to a view from a sailboat. In physics, the zoom is not through space, but through energy. The strength of a fundamental force, its coupling constant, is not a fixed number. It is a moving target. The electromagnetic force, for instance, grows stronger as you probe to higher energies, while the strong nuclear force grows weaker. This evolution is not chaotic. It follows a specific path, a flow through an abstract landscape that theorists call theory space. The stunning pattern that emerges is one of self-similarity, a fractal-like structure in these flows. The equations that govern how a force changes from the energy of a candle flame to the energy of a supernova are, in their mathematical heart, the same as the equations that govern its change from supernova energies to those near the Big Bang. It is a pattern that repeats itself across scales. Within this fractal flow lie special destinations, fixed points. These are energy scales where the forces stop changing, where they become perfectly balanced and stable. A fixed point is like a whirlpool in a river, a place where the flow seems to circle back on itself. Theorists believe that the entire cosmic history of our forces, from their unified origin to their separated roles today, can be described as a trajectory flowing from one fundamental fixed point in the past toward another in the future. The fact that these flows exhibit such elegant, repeating patterns is a powerful clue. It suggests that the wildly different laws of physics we observe at everyday energies, at nuclear energies, and at cosmic energies are not independent sets of rules. They are all connected, different facets of a single, deeper mathematical object revealed only when we understand how to zoom. The renormalization group flow is the hidden map that guides the universe's evolution, and its fractal beauty hints that the ultimate theory we seek may be the description of the most stable fixed point of all. The persistent appeal of a beautiful idea, even in the face of its absence, is itself a powerful clue. For decades, one of the most elegant frameworks in theoretical physics has been supersymmetry, or SUSY. Its core proposition is a symmetry of breathtaking simplicity, a kind of cosmic balancing act. It suggests that for every known particle of matter, a fermion like an electron or a quark, there exists a superpartner, a boson. And for every force carrier, a boson like the photon, there is a corresponding fermionic partner. This pairing creates a perfect mirror world, a hidden layer of reality where the two fundamental classes of particles are deeply intertwined. The most compelling reason to believe in this mirror world lies in its ability to solve the hierarchy problem with such effortless grace. Remember the Higgs boson, perched precariously on a knife's edge, its mass requiring an impossible cancellation of quantum fluctuations to remain light. In a supersymmetric universe, this is no longer a miracle. For every virtual particle that pushes the Higgs mass upward, its superpartner provides an equal and opposite push downward. The two contributions cancel each other out automatically, as a natural consequence of the symmetry. The fine-tuning vanishes, replaced by a deep and satisfying naturalness. The universe is no longer balanced on a pencil's tip in a hurricane. It is a ball resting securely in the bottom of a valley, its stability guaranteed by the very architecture of reality. This theoretical elegance is the pattern, a siren song that has guided a generation of physicists. The fact that such a beautiful solution exists, one that resolves not only the hierarchy problem, but also offers a compelling candidate for dark matter and points toward the grand unification of forces, creates a powerful intellectual current. The continued search for SUSY, despite the null results from the Large Hadron Collider, is not stubbornness. It is a testament to the belief that the universe should prefer such simple and beautiful answers to its deepest puzzles. The pattern is not in the data, but in the human conviction that nature's underlying order must be founded on principles of harmony and balance. Yet this drive for a single, elegant theory confronts a cosmic puzzle of almost unimaginable scale. String theory, perhaps the most ambitious framework for a theory of everything, proposes that the fundamental constituents of reality are not point-like particles but unimaginably tiny, vibrating loops of energy. The different vibrational patterns of these strings would give rise to every particle and force we observe, a beautiful and unified vision. But this elegance comes with a staggering consequence, a landscape. The mathematics of string theory does not point to one unique universe with one set of rules. Instead, it suggests the existence of a vast, perhaps infinite, collection of possible vacuum states. The number is so large it defies comprehension, often quoted as 10 to the power of 500. That is a 1 followed by 500 zeros, a number that dwarfs the count of all the atoms in the observable universe. Each of these possible vacuums represents a stable configuration of the extra dimensions string theory requires, and each configuration corresponds to a universe with its own unique set of physical constants. In one universe, the force of gravity might be repulsive. In another, electrons could be heavier than protons, preventing atoms from ever forming. Our universe, with its specific, life-permitting numbers for the strength of forces and the masses of particles, would be just one tiny, fertile valley in an endless cosmic archipelago of possibilities. This is the string theory landscape. The pattern here is not a single equation, but this overwhelming multiplicity. It offers a dramatic answer to the mystery of fine-tuning, the anthropic principle. We find ourselves in a universe with constants suitable for life, not because it was designed that way, but because an unfathomable number of universes exist, and we can only arise in one of the rare ones where the numbers are just right. But this solution presents a profound challenge for science itself. If every possible set of laws exists somewhere, how can string theory make a unique, testable prediction about our own world? The search for a deeper order then transforms. It may not be the discovery of one single set of equations that describe our universe, but the uncovering of a meta-law, a higher principle that governs the entire landscape and explains why such a multiverse of possibilities must exist in the first place. The holographic principle presents a universe that is simpler at its core. But how could such a radical idea ever be tested? The answer lies in a mathematical discovery so powerful it has reshaped modern physics, a pattern known as the CFT Correspondence. At its heart, this is a dictionary. It translates the language of one kind of world into the language of another, completely different kind of world. On one side of this dictionary is a universe with gravity, described by string theory living in a special kind of curved space called anti-de Sitter space. This space has a distinct boundary, a kind of outer shell. On the other side is a universe without gravity at all, a quantum field theory that lives only on that boundary. The stunning claim of the correspondence is that these two descriptions are exactly equivalent. They are two different ways of describing the very same reality. Every event that happens in the gravitational, three-dimensional bulk of the space has a perfect mirror in the interactions of particles on the two-dimensional boundary. A black hole collapsing in the interior is exactly the same as a specific state of a hot, dense plasma of particles on the boundary. This is not a vague analogy. It is a precise mathematical equivalence that allows physicists to solve problems in one realm by translating them into the other. A calculation that is impossibly difficult in the gravitational theory might become straightforward in the quantum field theory, and vice versa. This duality is a pattern of breathtaking utility. It has provided deep insights into the behavior of exotic states of matter, like the quark-gluon plasma created in particle accelerators, by modeling them as black holes in a higher dimensional space. But its greatest significance is as a fundamental clue. It demonstrates that gravity, the force that shapes the cosmos, and quantum mechanics, the rulebook for the small, are not separate, competing theories. They are inextricably linked, two faces of a single, deeper structure. The CFT Correspondence is a working model of the holographic principle in action, a concrete blueprint for how our rich, three-dimensional experience of spacetime could be a magnificent projection from a simpler, two-dimensional reality without gravity at all. The very stage upon which all these particles dance may itself be an illusion. We have always thought of space and time as the ultimate backdrop, the fixed canvas upon which the drama of the universe is painted. But a radical new pattern suggests this canvas is not fundamental at all. It is a tapestry woven from something far more basic. In theories like loop quantum gravity, the smooth continuity of spacetime dissolves into a frenetic network of tiny, discrete loops. Picture these loops not as objects in space, but as the very threads that create space. They connect to form a shimmering web of relationships known as a spin network. In this view, a volume of space is not an empty container. It is the number of loops within it. Time is not a flowing river, but the sequential flipping of the quantum states of this network. The three-dimensional world we move through is a collective hallucination, a pattern that emerges from countless individual threads, much like the smooth image on a television screen emerges from the frantic blinking of millions of individual pixels. The most compelling evidence for this emergence comes from the most extreme environment imaginable, a black hole. When physicists calculate the entanglement entropy of a black hole, a measure of the quantum information shared across its event horizon, they find it is not proportional to the volume inside the horizon, but to the surface area. This is a direct signal that the fundamental degrees of freedom, the true atoms of reality, live on a two-dimensional surface. The three-dimensional interior, with its depth and structure, is a projection, a hologram generated from the information encoded on the boundary. This means that what we experience as a particle moving through space might actually be a complex transformation in a lower dimensional system that has no concept of location or distance at all. The order of spacetime, with its reliable geometry and causality, would then be a secondary phenomenon, a stable pattern that crystallizes from a more primitive, non-spatiotemporal reality. This is perhaps the ultimate hidden order, a level of existence so fundamental that the very ideas of here and there, before and after, simply do not apply. We are like characters in a video game, convinced we are exploring a vast world, unaware that our entire reality is built from lines of code in a dimension we cannot perceive. Yet this emerging tapestry of spacetime confronts its most intimate mystery the moment we try to look at it. The quantum world holds one rule above all others. A particle like an electron can exist in a blend of all its possible states at once, a condition known as superposition. It is only when we attempt to measure it, to pin it down with a detector, that this ghostly cloud of possibilities seems to collapse into a single, definite reality. This is the quantum measurement problem, and the pattern is not a flaw but a feature, a process so consistent and reproducible that we build computers upon it. Yet its fundamental nature remains utterly opaque. We know what happens with perfect predictability, but we have no agreed-upon explanation for why it happens. What is the trigger that forces the universe to make a choice? The conventional interpretation, the Copenhagen interpretation, offers a pragmatic answer with profound consequences. It simply states that the act of measurement by a classical instrument causes the collapse. But this raises a deeper question. Where is the line between the quantum system and the classical measuring device? Is a single atom a quantum object, but a camera made of trillions of atoms is not? This seems arbitrary, a recipe for calculation rather than a description of reality. This ambiguity has spawned a landscape of competing ideas, each seeking the hidden order behind the apparent randomness. One compelling proposal is decoherence. This suggests there is no sharp moment of collapse. Instead, a quantum system is never truly isolated. It is constantly buffeted by its environment, by stray photons and air molecules. These countless tiny interactions effectively leak information about the system into the wider world, erasing the delicate superpositions. The system appears to collapse because it becomes inextricably entangled with its surroundings. It is not that the electron chooses a path, but that the path of the electron and the state of the universe become one single, tangled reality. This is a powerful idea, but it does not fully solve the problem, it just pushes it outward, distributing the mystery across the entire cosmos. Other theories are more radical. Pilot wave theory proposes that particles are real, point-like objects that are guided by a hidden wave, a subtle field that contains all the possibilities. The particle itself has a definite position at all times, but we cannot predict its path because the guiding wave is hidden from us. The strange statistics of quantum mechanics emerge from our ignorance of this deeper, deterministic reality. Then there are objective collapse models, which suggest that superposition is inherently unstable. They propose a small, spontaneous probability for a wave function to collapse on its own, a probability that becomes significant only for large, massive objects. This could mean that gravity, the force we experience every day, is not just a curvature of spacetime but the very mechanism that pins reality down, ensuring that cats are never both alive and dead, and baseballs always follow a single path. The most mind-bending possibility is that consciousness itself plays a role, that the awareness of an observer is the final ingredient that crystallizes possibility into actuality. While this idea is controversial, it forces us to confront a staggering implication, that the universe may not have a definite history until a conscious mind looks back upon it. The quantum measurement problem is the ultimate confrontation between the world of the tiny and our experience of a single, solid reality. It suggests that the act of seeing, of knowing, might be woven into the fundamental laws of the cosmos, and that any deeper order must finally explain the observer who seeks to discover it. This overarching pattern of fine-tuning is the grand finale of our cosmic detective story, the clue that encompasses all others. Each of the 40 anomalies we have explored, from the muon's wobble to the proton's stability, is a piece of a larger puzzle pointing to a universe that is curiously fit for life. The fundamental constants of nature, like the strength of gravity, the mass of the electron, and the power of the nuclear forces, are not random numbers. They are the dials on the universal control panel, And the astonishing fact is that these dials are set with impossible precision. If the strong nuclear force were just a few percent stronger, hydrogen would fuse too rapidly in stars, burning them out in a cosmic flash. If it were slightly weaker, complex atoms could never form. If the cosmological constant were not so infinitesimally small, the universe would have either collapsed back on itself immediately or flown apart too quickly for any galaxy to ever coalesce. The list of these delicate balances is long and profound. It is as if the universe was constructed with a specific outcome in mind, an outcome that includes us. This is the anthropic principle, the observation that the laws of physics seem uniquely tailored to allow for the existence of observers. But what does this mean? Is it mere coincidence, or is it a signature of design? The multiverse offers a powerful, if humbling, explanation. In this view, our universe is just one bubble in an infinite, bubbling froth of cosmic landscapes. Each bubble has its own random set of physical constants. In the overwhelming majority, the numbers are wrong, and those universes remain sterile, empty, or fleeting. But in an exceptionally rare few, like ours, the numbers line up just right. We find ourselves in a hospitable universe not because it was made for us, but because we could not exist anywhere else. Our presence here is a form of cosmic selection bias. Yet, the multiverse is not the only possibility. The fine-tuning could also be a profound clue pointing to a deeper, more unified theory. One where the constants are not free parameters but necessary consequences of the theory's internal logic. In such a framework, the values we see would be the only possible values, emerging inevitably from a single, elegant equation. The universe would be life permitting not by accident, but by necessity. This pattern connects the quantum realm to the cosmic scale, and even to the biological world, suggesting that the emergence of complexity and consciousness is not a fluke but a fundamental feature of a cosmos whose deepest laws are somehow aligned with the potential for life. These 40 threads, when woven together, begin to form a tapestry far grander than any single anomaly could reveal on its own. The extra wobble of the muon is not just a curiosity. It is a direct signal that unknown particles are influencing our world. Those very particles could be the same superpartners that supersymmetry proposes to naturally stabilize the Higgs boson, solving the hierarchy problem in one elegant stroke. The profound mystery of our matter-dominated universe, the asymmetry that allowed galaxies to form, is deeply entangled with the strange behavior of neutrinos and the heightened levels of CP violation seen in particle decays. Perhaps the same heavy, right-handed neutrinos that gave mass to their ghostly cousins also decayed asymmetrically in the early universe, tipping the scales forever. Even the most baffling fine-tuning, the impossibly small energy of the vacuum, finds a potential resolution in the holographic principle. If our three-dimensional reality is a projection from a two-dimensional boundary, then the cosmological constant problem might be an illusion, a consequence of our limited perspective within the projection. The stability of the proton, the anomalous magnetic moment of the electron, the rare decays of B mesons, each one is a single instrument in a vast cosmic orchestra. They are not playing random notes, but different parts of the same symphony, a composition whose full melody we have not yet heard. While a single, simple equation that encapsulates all of reality remains the Holy Grail, these patterns collectively tell us something just as important. They reveal that our standard model, for all its spectacular success, is not the final word. It is an effective theory, a user manual that works perfectly well for the world we see every day, much like Newton's laws of motion work for baseballs and rockets. But just as Einstein's relativity revealed a deeper truth behind Newton's clockwork universe, these 40 clues are the unmistakable signs that we are standing at the edge of a similar revolution. Our current rules are a low-energy approximation, a shadow cast by a far more elegant and profound underlying order. The cracks in the foundation are not signs of collapse, but windows into a brighter, more complete understanding of everything. Our journey through these 40 patterns reveals a universe whispering secrets just beyond our current understanding. From the wobbling muon to the cosmic lithium shortage, each anomaly is a potential crack in the facade of known physics. These are not flaws in the machine, but glimpses of the deeper, more beautiful machinery operating beneath the surface. The pursuit of these patterns is far more than an academic exercise. It is a fundamental human endeavor, a direct continuation of that ancient drive that led Democritus to stare at a slab of marble and wonder about its smallest parts. We are driven by the same need to comprehend our place in the cosmos, to read the hidden language of reality. The very fact that these puzzles exist at all is a powerful testament that our current map is incomplete, that there is infinitely more waiting to be discovered. The next great breakthrough in physics may not come from a single, monumental experiment, but from the subtle art of connecting these disparate dots, of seeing the grand symphony in the scattered whispers. Which of these patterns do you find most compelling? Is it the ghostly signal from the galactic center, the stubborn stability of the proton, or the profound fine-tuning that allows for our existence? Share your thoughts in the comments below, and do not forget to subscribe for more deep dives into the mysteries